Hello, my name is Ashton Woods. I'm a geologist with the United States Geological Survey at the Earthquake Science Center in Menlo Park, California. I'm very pleased to be lecturing today on flooding hazards in Indonesia, and I ask for your patience as I share my screen and we can continue with the lecture. Lecture 7, Flooding Hazards in Indonesia. Indonesia is prone to various disaster types that have steadily increased frequency within the last 10 years. Many global initiatives tend to focus relief efforts in Indonesia during seismic, volcanic, and tsunami-related disasters. However, our focus today is on the hazards that can exist as either a primary or secondary effect during a disaster event. Data obtained by the World Bank in collaboration with the Indonesian National Board of Disaster Management contributes floods as the leading cause for population displacement in Indonesia. Annual disaster trends beginning in early 2000s suggest that the frequency of flood-related disasters across Indonesia are rising exponentially each year, with the reported affected population exceeding 5 million in 2019. In fact, socioeconomic impacts and climate variations projected for 2050 indicate that the minimum affected population annually from riverine flooding is expected at just under 3 million. The expected costs related to infrastructure damage following a flood event within this projection could cost the Indonesian government 50 billion USD or 750 trillion Indonesian rupiah by 2050. Here the unit G is representative of billions in USD, or the US dollar. It is interesting to note that the climate change as a driver plays a significant role for affected populations in the projection of 2050, while socioeconomic impacts are responsible for almost all of the costs for damages. Here's a comparative report on the influence of riverine versus coastal flooding to annual damage cost in relation to resiliency calculated by the flood protection level. The FPL ranges from 1 to 15 in this example, where the higher the FPL, the greater resiliency against flood potential. For riverine flooding, or floods related to inland water bodies such as rivers, channels, and lakes, the FPL is expected to rise by 2050 to level 12. This suggests that the government, private, and public authorities are implementing mitigation strategies to combat against flooding events related to terrestrial water sources. However, coastal flooding FPL for the year of 2050 is expected at level 2, representing that the lack of integrating new mitigation tactics and the destruction of natural barriers along the coastline is cause for vulnerability to coastal flooding disaster events. In fact, it is expected that the Indonesian government will see up to 79 billion USD dollars in urban and infrastructure damage, which is $23 billion more than the cost of damage from riverine flooding for that year. Indonesia is ranked as number 6 globally for having a population prone to flood-related disaster events. The table is ranked from 1 to 18, however the report ranks up to 156 countries. Indonesia ranks at number 6 on the table, which is curious as the Philippines, that share similar geographic area to Indonesia, is ranked at 16, or has a higher resiliency score compared to Indonesia. Resiliency scores are determined by the ability to reduce vulnerability of an at-risk population to natural hazards or disaster events. Here I have a video that will cover basic flood definitions and provide a quick overview of contributing factors that create ideal flood conditions.
Flooding happens when the water in a river exceeds the volume of its channel. The river cannot discharge the water quickly enough, so it overflows, flooding the surrounding land. A river travels through a drainage basin. Water in that basin drains into the river, which discharges it towards the sea. Drainage basins can have different sizes and shapes, which influence the flood risk. The larger the basin, the more water it will collect, and the higher the peak discharge of the river. If the ground of the basin is impermeable, excess water will flow quickly to the river, making it more likely to flood. The ground could be impermeable if it has been baked dry by the sun, is covered in concrete, like in a town or city, is comprised of solid rock, or if heavy rainfall has already saturated the ground. If a river has many tributaries, this increases the volume of water flowing into the river and increases flood risk. If a river basin is covered in dense vegetation, this can help to reduce flood risk by trapping the water as it flows down towards the river. Areas which have been deforested are more prone to flooding as this natural barrier has been removed.
One environmental factor I would like to delve further into is soil saturation and how it contributes to surface runoff and an increase of flood potential. Soil saturation is when the void space in the soil profile becomes filled by moisture, causing it to become sodden. During heavy rainfall, oversaturation of the soil prevents infiltration from occurring. As the water is unable to be absorbed into the soil, it acts as runoff. This is particularly true for compacted clay soils. The presence of argillic soil horizons are common across the islands of Indonesia. Argillic soils are high silicate clays that have been displaced by alluviation processes, more simply transported by rainfall. Red and yellow podzolic soil is also quite abundant, where podzolic soils are acidic and are susceptible to alluviation or leaching. The acidification of soils with a high clay profile within proximity of sedimentary alluvial basins presents limited soil stabilization from vegetation, allowing for more extreme flood frequency within floodplains. Determination of flood frequency requires an understanding of the floodplain. The floodway is the channel where river and floodwaters flow. The flood fringe is the limit of where floodwaters can extend during flash flooding. The example shows a 100-year floodplain and the extent of where floodwaters can extend during 100-year floodplains. The 100-year floodplain represents a 1 out of 100 or 1% chance that the floodplain will be submerged within a given year. For instance, in 30 years, for a 100-year floodplain, the chance of occurring annually would be at 26% within that 30 years. This percentage can be calculated by thorough site observation and the equation here on this slide. This graph represents the number of floods that have occurred in relation to annual rainfall in millimeters from the year of 2016 to 2019. The information was calculated by analyzing the distribution of precipitation from Sumatra, Java, Borneo, and Sulawesi. Rainfall averages declined rapidly between the years of 2017 to 2018, representative of drought conditions during these years, and the averages have since begun to increase. The flood events in 2019 far exceed the average of rainfall and is representative of tsunami activity. Closer inspection to more densely populated cities between these four islands of Indonesia, the average of precipitation, my apologies. The averages in precipitation between 2010 to 2019 are separated into months. There is no equal distribution between these cities, yet there is consistency indicative of extreme wet seasons to prolonged drought conditions that cause soil strain hydraulic gradients in tropical environments. This is a geological map that shows the age and rock types for Indonesia. For the purpose of this lecture, it will be used as a quick reference for the alluvial plains, seen here, where most Indonesian cities are located. We can track the significant changes by tracking surface anomalies of terrestrial surface and subsurface waters. The GRACE satellite, or Gravity Recovery and Climate Experiment Satellite, is one way to record these anomalies. The chart displays wet, or EWT, which is the water equivalent thickness data of terrestrial waters and their gravitational variations from 2015 to 2019. The spikes on the bar graph are indicative of heavy rainfall, while the missing data represents drought conditions for 2018. The map highlights areas of water storage changes from upstream river sources and is in relation to the GRACE data on the previous slide. Low-level changes indicate lack of flood outlets and significant increase of soil saturation. These are representative of the red on the map. These areas experience alluviation and vegetation reduction, which increases the vulnerability during monsoon season. On the opposite spectrum, there has been significant water storage depletion in the Banten province near Jakarta on the island of Java. This may be due to river remediation efforts and urbanizations within this area. Here it is represented as the yellow zone on this map. High-level areas can experience ground displacement following flood events. A closer inspection of ground displacement in Jakarta following riverine flood disasters for 2015 to 2019 is seen here. Sediment is rapidly bleeding into coastal waters, and the high tides and heavy rainfalls are causing Jakarta to sink. The delta is unable to withstand these density changes, and they're mostly caused by anthropogenic and environmental interference. Here we look at a flood event in Jakarta on the Siliwangi River during January of 2020. As you can see in the image to the right, there was extensive flooding into the neighborhoods surrounding the river. The river resulted in flash flooding, but because of the sediment transport causing sediment load near the coastal water zones, there was no proper outlet for the floodwaters to recede, and so the water stood within the city for a few days. Poorer districts were strongly affected during this flood event in January. It was reported that there were 66 individuals that were killed, while 36,000 people were displaced due to property damage following the flood. Because there was a significant amount of roads that were blocked, emergency relief efforts and aid were very limited because there was no easy way of access to help the individuals that were displaced. This allowed for slope failures to occur as the floodwaters rose up above the embankment into the flood fringe. Sumatra is also experiencing similar problems as the surface is bleeding into coastal waters due to damage to peatland swamps from agricultural expansion. The Sumatra wetlands, flooding would normally be less prominent near cities located near the wetlands, as the wetlands and swamps act as a natural barrier. Because these barriers exist so close to the coastline, there's less damage during flood events. However, as agricultural expansion continues within these areas for palm plantations, these wetlands are being affected and more flooding is starting to develop on the island of Sumatra. The urbanization in these areas is also causing more susceptibilities for drought and fire conditions to occur. Representing the next few slides that will follow will show how the export trade influenced the flood potential due to the damage of these wetland areas. The map shows the agricultural usage of the island of Sumatra in relation to undisturbed and rainforest areas that are not densely populated. The slash and burn agriculture that's occurring in these areas because of illegal plantations for palm trees is causing serious damage to the swampland. The flooding events in these areas are becoming more and more progressive because the swamps are starting to disappear in these areas. It's also due to the amount of fires that are happening in Sumatra because of the oil palm plantations within the wetland areas, as the swamps are rich in organic deposits or in peat. Here we see the organic carbon deposit map on the right-hand side, showing a high density of vulnerable soil organic carbon. Peat is known to burn for months at a time, and so damage to the peatlands along the coastal areas of Sumatra are causing issues with the wetland health. Wetland health allows for more flood potential and an expansion of the floodway and flood fringe. Sumatra can expect an increased level of flooding to occur in the future. Here we see an image of Semarang on the island of Java. After a coastal flood event where the tidal waters have entered into city neighborhoods, have damaged several of the levees, and have infiltrated into the agricultural zones along the coastline. The Nature Conservancy and the Global Disaster Preparedness Center are working in collaboration with Semarang on creating different types of flood maps so that the city is more capable of understanding how coastal flooding following heavy rainfall and high tide events will damage the local area. This is an example of flood information collected from July of 2019 to July of 2020. That the floods that have occurred in this area have caused significant damage and have displaced a majority of the population. Between this year, 537,000 people have been affected by the flooding, and they've had significant damages to 14 hospitals, which normally act as evacuation zones. The tourism in these sites have also significantly decreased, and there have been some issues with how much agricultural land has been contaminated due to brackish water inclusion into the groundwater. Semarang believes that the reason for the flooding, particularly from standing water following a flood event, is due to the reduction in mangroves along the coastline. However, closer inspection into the city has revealed within this past year of data from the Nature Conservatory and the Global Disaster Preparedness Center that there is just no proper drainage for the storm waters to recede. They expect that Semarang is going to experience increased levels of flood activity, and there will be more significant damages following the year of 2020 should the city planning not accommodate to future flood disasters. Information in this chart shows different factors that contribute to increased damage and cost of damages following flood-related disasters in urbanized areas. With the top of the pyramid showing that outdated mitigation tactics and an absence of communication between agencies can cause vulnerability and lead to a more affected population following the year of 2020. Other factors that are included in worsening flood conditions are lack of investigation into the floodplain, urbanization on top of the floodplain, deforestation activities, poor location choices for installation projects of mitigation tactics, improper debris removal, and inaccurate site inspections. Flood maps are an important mitigation tool that should be utilized by the cities located in the coastal regions of Indonesia, as it will help city planners and emergency managers to better understand how to properly evacuate these zones, as well as where to reduce urbanization efforts and increase mitigation tactics along riverine and coastal areas. Here I'll quickly explain the definition for each section of the flood map. Here I'll explain the basic definitions of flood maps as defined by the Federal Emergency Management Agency in the United States in the Flood Insurance Program. SFHA is the Special Flood Hazard Area. These are areas where federal and local agencies determine potential risk to the local community. FIRM stands for Flood Insurance Rate Map, which we use here in the United States as a way to involve the community in understanding that they are existing within a potential flood zone where there will be a higher frequency of flooding following heavy rainfall events. The NFIP, which is the National Flood Insurance Program, is a federal insurance policy that determines which building codes need to be implemented in which zones within the city. And the FSI, or the Flood Insurance Study, which is also known for Flood Risk Data Study, reports on the water hazards within this specified area and allows for site inspections to improve onto flood maps. Emergency managers and city planners know how to properly zone each part of the city based off of flood potential. Flood mapping is important for understanding how to properly mitigate in urbanized areas, especially when inundated streets become a problem. Inundated streets are a significant issue reported in Indonesia, where the roads become false rivers or artificial rivers following heavy rainfall or following a tsunami event. When the roads become blocked or when they become submerged, there becomes limited availability for emergency services to be provided to the affected population, and this can increase the potential for deaths to occur due to flooding incidences. A good mitigation tactic that is being utilized in different parts of the world are prefabricated roads. There have been significant studies on prefabricated roads in Japan, as well as the Netherlands and the United Kingdom, and are starting to be brought into the United States as a preventative tactic for artificial rivers on roads. This diagram shows the breakdown of prefabricated roads based off of each individual panel. What we're staring at in this image is one panel deconstructed so that we can see the multitudes of layers that go into this mitigation tactic, with number one being the road panel itself, which can be made out of asphalt or it could also be made out of plastic material. These panels can be switched out or interchanged should they suffer from any damages, and normally have a great system that leads to number two, the secondary panel, which is a mesh panel that catches larger bits of debris. Number three is the mortar or the synthetic resin that attaches the secondary panel to the flood pipe and the RC base, which is representative of number 4 and number 5 on the diagram. The flood piping takes the water that's being drained through the grates and being filtered through the mesh and transports it out into a designated drainage area. Prefabricated roads allow during a tsunami event or heavy rainfall to present an outlet for drainage so that the roads are available for emergency service providers and emergency aid to access individuals that are being affected by the flood without blocking the roads or submerging the roads. Here's an additional mitigation tactic that is being explored into. There are plans to implement this in Wales and the United Kingdom, and other countries around the globe are considering using tidal lagoons as And other countries around the globe are also in consideration of tidal lagoons following the extensive studies. It's a recent technology that requires the construction of a breakaway wall. Attached to the breakaway wall is the turbines, or attached to the breakaway wall is a sluice gate, and on the inside of the sluice gate is a turbine. Essentially what happens is the breakaway duration of tidal lagoons following the extensive studies. It's a recent technology that requires the construction of a breakaway wall. Attached to the breakaway wall is a sluice gate, and on the inside of the sluice gate is a turbine. The tidal lagoon is a mitigation tactic that is supposed to reduce the damages, that is supposed to reduce flood damage caused by high tide and tsunami events. It is known as a coastal zone management project. Here's a closer inspection of the sluice gate along the breakaway wall, where on the left we see the ocean water, and on the right we see the lagoon. There are two sluice gates, one facing the ocean and one facing the lagoon, and there is a turbine that flows in and out. So say a tsunami warning has been issued and both sluice gates are up. Instead of giving more traction and more draw, instead of giving more draw of water for tsunami development, one could simply close the sluice gates on either side, keeping the waters within the tidal lagoon. This prevents the tsunami from drawing the water out of the lagoon and away from the coastline. The wave generation is then significantly reduced. However, there are disadvantages to the tidal lagoon that are similar to that of levees that are used now, whether they be man-made or earthen-based levees. There is the problem of whether or not it can be seen as a long-term solution. And there's also the issue with maintenance and the cost of maintaining tidal lagoons. The significant problem with tidal lagoons that are so similar to levees, however, is that it can increase flood risk elsewhere during tsunami and high tides. The video that I'm about to show is going to explain how levees in one area can cause a higher flood risk potential in other areas that are not being protected or have smaller levees, thus explaining further similar issues that could be experienced with tidal lagoons should they be implemented near coastline cities.
People love levees. There's about 100,000 miles of these embankments across the US, sometimes concrete, sometimes earthen. For centuries, we've built them between humans and rivers. Even when levees are effective, they can still be devastating. As far back as 1852, levees came with a very important warning. Charles Ellet Jr., a famed US civil engineer, cautioned that levees confine rivers and cause them to rise higher and flow faster. And relying on levees encourages a false security. But he was largely ignored. Levees became the default for flood control, mostly funded and constructed by local entities. Some riverside communities that could afford it built taller levees for more protection, while less fortunate neighbors dealt with the devastating effects. To show you what we mean, we went to the banks of the Mississippi River, to a fluid mechanics lab where a team of engineers from the University of Minnesota built us this landscape model to test flood scenarios. Overhead, a scanner collects 3D data to measure exactly what's happening. It's a generic model of a river with no levees. That means when the water level increases, it overflows and spreads across the floodplain, often creating important wetland habitat that's home to a variety of species. Putting in levees cuts rivers off from this land, destroying floodplains and wetlands. It allows people to convert these areas into farmland or build houses on them. And while levees protect these communities from flooding, they constrict the river into a narrow channel, making the water flow faster and higher. That creates a bottleneck leading to additional flooding upstream. If all levees are the same height, both sides should be about equally protected from the average flood. And if the river rises so much that the water overtops the levee, then both sides should flood pretty equally. But let's say people on one side of the river lobby for higher levees. Now, instead of both sides flooding, only one floods. The side with the lower levees is at a clear disadvantage. So what can people in flood zones do? We can't just pick up and move major cities. We need levees to protect places like these. There is an alternative. We could build levees farther back so rivers could still expand and create wetlands. These setback levees ease flooding on both sides rather than protecting one city at the expense of another. This approach is common in other parts of the world, like Holland, for example, but not in the US. Here, we tend to build levees right next to rivers. Some communities that can afford to build higher levees do so at the risk of others with little oversight. We do have the Army Corps of Engineers, a federal agency tasked with regulating a fraction of all levees. They have to ensure, at least on paper, that federal levees won't dramatically raise local flood levels. But those engineering predictions don't always match reality. For instance, the Army Corps designed Valley Park's levee in the early 90s with data and software from that era. Engineers estimated the levee's impact on neighboring areas would be minimal, but by the time it was completed in 2005, the region had grown significantly. More people had built alongside the river, increasing the risk of flooding, which wasn't considered in the original plan. While we don't know the precise impact of Valley Park's levee on neighboring towns just yet, since the levee was built, the region outside Valley Park has suffered 2 of the worst floods in its history. The Army Corps says they've done nothing wrong and that the levee meets all state and federal laws. But there's a growing body of research that shows levees push flooding onto surrounding communities that have lower levees or no levees at all. Researchers measured water levels around 13 levees in the Midwest and found they all increased flooding, some by over 5 feet. As the climate changes and cities push for higher levees, flooding is only expected to get worse. Even though the science overwhelmingly shows that constructing higher levees makes flooding worse in the long term, we keep building them taller, passing our problems upstream.
If it keeps on raining, levee's going to break.
So let's summarize. In the past 10 years, it is evident that socioeconomic impacts are responsible for the increase of flood potential. However, we should not exclude out that as we are nearing 2030, that climate impacts are also contributing to the possibility of more flood-related disasters within Indonesia. The destruction of natural barriers along the coastline and in wetlands is also responsible for the increase of flood potential, as we see a significant amount of sediment transport in the coastal waters, leading to density changes beneath the surface, causing cities to sink within the alluvial basins. And finally, in order to increase resiliency in Indonesia following flood-related disasters, one must understand the local stratigraphy alongside with the importance of site inspections and flood zone mapping to better understand where to implement mitigation strategies and tactics to help decrease the level of damage and the cost of damages for future flooding events. This concludes our presentation. Thank you all for your patience and your commitment to the lecture today. Remember, during the coronavirus, we must stay vigilant and maintain our health so that way we can continue to help others in the future. So please remember to always wear your mask, social distance, and stay safe.